sustainability across the globe. This virtual seminar series is being organized by CompSusNet with support from the National Science Foundation and Cornell University. My name is Doug Fisher, and I'm the Director for Outreach, Education, Diversity, and Synthesis of CompSusNet. I and other members of the outreach team, which includes Carla Gomes, Christiane White, and Rich Bernstein, schedule talks on computational sustainability regularly and post them to the URL given on this slide. In 2 weeks, Professor Tanya Berger-Wolf of the University of Illinois at Chicago will be speaking. During the webinar, you can ask questions through the question and answer facility or the chat window on Zoom, which will be related to the speakers' allows. We may wait until the end of the presentation to raise questions, but very typically we raise them during the talk itself. In fact, if you want, go to the chat window now and say hi to all the attendees so you can easily find where it is. CompSusNet has several social media outlets, including Facebook, Twitter, LinkedIn, and the CompSusNet blog on our website. So today we're thrilled to have two researchers from Microsoft Research. Doctors Ranveer Chandra and Sudipta Sinha. Dr. Chandra is a principal researcher at Microsoft Research, where he's leading an incubation on IoT applications, and he received his PhD from Cornell University. Dr. Sudipta Sinha is a researcher at Microsoft Research, and he received his PhD from the University of North Carolina, Chapel Hill. And if you look through their bios, they're doing lots of exciting things, and we are looking forward to hearing about some of those today. So Ranveer and Sudipta, do you want to take it from here? Unmute your mic.
Hello, everybody.
Hi, I'm Ranveer.
Yes, Sudipta.
Yeah.
Can you hear us, see us?
Yes.
Wonderful. So we'll get started with the presentation, and feel free to just okay. Yeah, do you see the screen?
Yes, we do.
Okay, wonderful. So we can get started, right?
Yeah.
So hi. So today we'll talk about Farmbeats, which is an AI and Internet of Things system for agriculture. This is a project we started here at Microsoft in 2015, around the same time, 3 years back. And you all know a lot about Microsoft Research, I guess, otherwise we would have given a background. If you're interested in that, let us know, and I'm happy to chat more about what Microsoft Research is, what all we are doing. But this particular project is part of one of the things we have encouraged in Microsoft Research is to think 5-10 years down the line, what would be the big disruption? And that is what got us started on this project. In particular, what we are trying to solve in this project is we are trying to go after the world's food problem. The world's food production, as many of you know, needs to increase by 70% by 2050 to feed the growing population of the world. And this is just just feeding the world. But if you think of, I was at another panel with the Rockefeller Foundation, and there was a lady there who said, well, we've been talking about feeding the world, but talk about nutritioning the world. That's providing nutritious food. And what does that take, right? So we are up with a big food challenge. Like, we need something like the Green Revolution all over again. The key question is, how do we get there? How do we get to this increased food production? Previously, the Green Revolution helped us get over this bump back in the late 60s, early 70s. What is it that's going to take us to the next level here? So agricultural scientists have been looking at this problem for quite a while. And if you, in the last 30 years, they've come up with various techniques. And the most promising approach to solve this food challenge is that of data-driven agriculture. What do we mean by data-driven agriculture? What we mean is the ability to map every farm in the world and overlay it with lots and lots of data. That is, for example, what is my soil moisture level in this farm 6 inches below the soil? What is the soil nutrient level? What is the soil carbon level? If you can come up with these kind of maps, this can enable various techniques one such technique is that of precision agriculture. So what we mean by precision agriculture is, so this is something which you already know, but people working in ag would know what precision agriculture is. Basically what it refers to is site-specific application of the input materials. For example, rather than applying water uniformly throughout the farm, you could apply water only where it's needed. If you had maps like this, you could apply nutrients, nitrogen only where it's needed, pesticide only where it's needed. And precision agriculture as an approach has been shown to improve yield. Like, for example, you could plant seeds closer together in the more fertile parts of the farm. It helps reduce cost. That is, you'd use less water, less pesticide, less fertilizer. And it's also better for the environment. You're not wasting water. You're not causing any nitrogen leaching and so on. The other, if you could build maps like this, so once we started doing this, we got lots of requests from seed companies where they were like, this kind of a map can help build, help with phenotyping. I was at an ARPA-E event on Wednesday where we were presenting this, and there were seed companies there too who think that once you could build maps like this and you can argue, why did the seed grow differently in different parts of the farm? The same seed variety, why did it give different yields in the red and the blue parts of the farm? In the rest of this talk, we'll primarily talk about precision agriculture, but you can easily see how if you could build maps like this, it would translate to phenotyping as well. So precision agriculture as a technique was proposed back in the 80s. We are not the ones inventing it. But it's been 30 years since then, and precision agriculture still hasn't taken off. Its adoption is still very, very limited. And according to the USDA, the biggest reason precision agriculture as a technique hasn't taken off is because of the high cost of data-driven farming solutions. Just getting this data is super expensive. Just to give you an idea of how expensive this is, there was an expo at UC Davis I was attending 1.5 years back, and there were several companies who were presenting their precision ag solutions. This is the latest and greatest sensors. And the cheapest sensors that were available at that event were 5 sensors for $8,000 and a recurring cost. And all they were doing was measuring soil moisture. And this is the cheapest. There were others who were much fancier, but much more expensive. For a farmer to invest that kind of money, like thousands of dollars for just a few sensors without knowing what is the ROI, what is the return of investment on this, is asking for too much. So that is the goal of the Farmbeats system. The goal of the Farmbeats system is to bring down the cost of data-driven agriculture solutions by 2 orders of magnitude. We want to bring it down from 8,000 to 80. That is what we are trying to achieve. So let me start by telling you, if you wanted to build an accurate map, like for example, you wanted to overlay this farm with data about this is the soil moisture map 6 inches below the soil, how would you go about building such a map? Well, the state of the art would be you'd say, well, we'll put lots and lots of sensors. We are going to connect them to the cloud over some connectivity solution, send all this to the cloud, and then you can build a very accurate map. This is how your Amazon Echo system, Alexa system, or your Google Nest, or whatever system you're using, your Xbox at home, they all work this way. They all send all the information to the cloud where you do the computation and come back with the results. The thing is, an IoT system for agriculture wouldn't really work this way because of 3 key challenges. The first challenge is that of internet connectivity. That is, most of these farms, even in the US, do not have any internet coverage. Some of them, even if they have connectivity, when you plant the seeds, by the time the crops grow, the connectivity is lost. And this is one of the primary reasons existing solutions, sensor solutions, are so expensive. That is, they end up using either satellite or custom cellular solutions to connect the sensors to the internet. And this is one of the biggest problems with IoT systems for agriculture. The second problem is there is no power on the farm. That is, most of these farms, they don't have power outlets in the middle of the farm to connect your devices. You could think you could use solar power to connect these sensors, but you had to be in Seattle the last winter to see why that wouldn't work. We had a really cloudy winter. You all know how Seattle is, and last winter in particular was really bad. The third problem is that of limited resources. That is, if you wanted to build an accurate map of the farm, you would need lots and lots of sensors. But putting lots and lots of sensors, because for example, just to give you an idea, it's well known that soil moisture has a significant variation even within an acre of the farm. Similarly with soil nutrients. So if you wanted to build an accurate precision map, this heat map for the farm, you would need lots and lots of sensors. But putting lots and lots of sensors is expensive to deploy, to manage. It will also come in the way of the farmer due to the as a farmer does the day-to-day job. So this is what Farmbeats does. It's an end-to-end system that's able to ingest data from sensors, drones, cameras, push them through Farmbeats, and provide these farm services. And in the process, it solves the problems that we talked about: connectivity on the farm, limited sensor placement, internet connectivity to the farm, and so on. And we've done a few deployments that we'll talk in the end. So let's start by the first one, network connectivity on the farm. So the biggest, so the problem is the following. That is, the farmer's house typically has some sort of connectivity to the cloud. They pay for broadband, but all they get is 1 to 3 megabits a second. But the actual farm could be a few miles away. It could be obstructed by crops, and the connectivity could be obstructed by crops, and so on. So how do you get these farms connected? How do you connect sensors, cameras, tractors, drones to the farmer's house from the farm, which is a few miles away? To solve this problem, we use a technology called the TV white spaces. This was a research within Microsoft Research. I started this effort in 2005, where the key thing with the key idea of TV white spaces, what it enables is the following. Suppose you buy a Wi-Fi router from Best Buy and you plug it into your house. And imagine if you could access it a few miles away. Now that's cool, right? Right now, your Wi-Fi connection just drops off right as you exit your house. With this, if you could access it a few miles away, that could be super disruptive. And the key way we enable this is the key technology we built here, which got the Best Paper Award in ACM SIGCOMM in 2009, was we were able to take a Wi-Fi signal and put it in an empty TV channel. You know how, so when you browse, this is over-the-air TV. You know, when you browse over-the-air TV, you see certain channels where there is a transmission going on. The other channels are empty. All you see is white noise. Like, there's nothing going on those TV channels. The particular technology we developed was to take that Wi-Fi signal and put it in an empty TV channel such that it doesn't interfere with the TV reception on an adjacent channel. So imagine a scenario where on channel 7, you could be watching NBC, and on channel 8, we could be broadcasting Wi-Fi. And the reason this is so cool is that compared to Wi-Fi in the lower frequencies, the TV frequencies are lower in the frequency spectrum. Compared to Wi-Fi at the same power level, in UHF frequencies, your UHF TV channels, your signals would go 4 times farther. In VHF, they would go 12 times farther. And this is in free space. Once you put in trees, crops, canopies, buildings, even in our latest experiments, even in soil, your signals just keep going through. Its propagation is much, much better. So just to give you an idea of how this works in one slide, I'm trying to put in 5 years of our research into this. So this is the way, this is the reason why this technology is different from other technologies in this space. So suppose this is the y-axis is power, the x-axis is frequency. Suppose at wherever you're sitting right now, these are the TV channels that are transmitting. These are the TV channels. If you brought a TV with an over-the-air antenna, you'd be receiving these channels. The way a TV white spaces system would work is it would first figure out what are the TV spectrum, TV channels that are not in use. It would then transmit in those available frequencies. While it is transmitting, it would keep listening to see if the TV transmission resumed. If it did, it would move to a new frequency. And if needed, it would adjust its bandwidth and power levels. Now, each one of these has multiple papers that we've written. If you go to our website, if you go to, you'll find in our research site, you'll find a lot of papers that were written in this space by us. So when we developed this system, we built the first network here at Microsoft campus. We showed that you could actually get really long range, high bandwidth connectivity. The FCC chairman came here in 2010 in August to see the demo we had put together. And in 2010 in October, this technology was made legal in the US. Since then, we've actually gone across the world and deployed this technology in various parts of the world, connecting rural parts of India, Africa, to the internet, high schools, hospitals, libraries, and so on. And we've received a lot of encouragement from our executive leadership. Our CEO, Satya Nadella, on the Windows 10 launch day was here in Kenya in a remote site making a call to another high school in India over the TV white spaces. These were two high schools that previously didn't have any connectivity. These guys were not connected to the internet and were able to connect using this particular technology, using the TV white spaces. And Microsoft in particular this year, last year in July, President Brad Smith made an announcement in, basically made this, he was in DC, and he launched an initiative called the Airband Initiative, through which Microsoft has made a pledge to connect 2 million rural Americans to broadband by 2022. This is in America. We are trying to provide rural broadband connectivity to rural Americans. And so these are all the different initiatives that are going on within Microsoft. Just to give you a recap, this is what we mean by the TV white spaces, the empty TV channels. And the key insight that we had for agriculture was that TV towers are where people are in cities. Like, for example, in Seattle, you'll have a lot of TV towers. In San Francisco, you'll have a lot of TV towers because there are people who watch TV. The farms are away from the cities. Because these farms are away from the cities, you have fewer TV towers around them. What that means is you have a lot more empty TV channels, a lot of empty TV spectrum. We are talking of hundreds of megabits, if not a gigabit per second of unused capacity that is available in the farms, not in the cities, but in the farms. At which point, we are not only talking of connecting sensors, you could be connecting drones, cameras, tractors. You could be sending a lot of data that previously wasn't possible. If you talk to agricultural scientists, most of them, one of the biggest pain points for agricultural scientists is the ability to get the data from the farm. With this technology, we believe we'll be able to overcome that barrier. Our vision is just like Wi-Fi connects your house, these TV white spaces can connect your entire farm. That's what we've been doing. We've been putting these antennas in farms and connecting miles around it. We have a deployment in New York, and in March, I'll be visiting Cornell, the ag school, as well as the CIS, and we look forward to starting some collaboration with Cornell on this technology, as well as the other parts of Farmbeats as well. At this point, I wanted to hand over to Sudipta to talk about the next parts of Farmbeats.
Right. Thank you, Ranveer. Hello, everybody. Can you hear me clear?
Yes, we hear you well.
Okay, good. So switching gears from networking to imaging. So just a brief background, I work in the area of computer vision, and one of the core themes of my research is how to map a scene in 3 dimensions from images, all kinds of images. And primarily for Farmbeats, what I've been involved in is investigating a lot of different approaches to do low-cost aerial mapping, and then analyzing these images to extract information that could be used then for other kinds of predictions. So,
Sudipta, do you mind if we ask a quick question before you launch into that?
Sure.
So there was a question from Noah wondering whether the long-range communication that I think was just being discussed is bidirectional.
Yeah, it is bidirectional. It is, and the longest links we have is, like, for example, in India, we have a link which is 10 miles, 16 kilometers at 2 megabits a second bidirectional.
One more.
Okay, what is that? Okay, I should. Where do you see that?
Here.
Okay.
Yes.
Yeah, so we did, so this is something that we are working with companies to develop. This is a specific device. This is a device that would operate in the spectrum. So we have a few now that are FCC certified, and those devices can be used in the US. These regulations are different in different countries. In the US, it is legal. It's legal in US, Canada, UK, Singapore, Philippines, South Africa, Malawi, several countries, but the others we are actively working on to make it, to work with the government. In a lot of countries, we are actually working with the government to get experimental licenses to show that it doesn't interfere with PB in those countries.
Okay.
So backhaul and then so.
What
Yeah.
else?
So usually
Yeah, go
what
ahead.
we do. Yeah. So the question is, so Yuvraj is asking, is the assumption? Yeah. So Yuvraj, nice to connect with you again. So yeah, that's what the assumption is, that you'll have these short range links. LoRa could also be a short range link, or you could have Wi-Fi, or you could have other techniques to get this data and then send it over the TV. Right. So we'll cover that after Sudipta. I'll come back to talk about how do we do the data collection from the farm.
Okay, thank you.
Okay. We go back to full screen. Okay, so the next part of the talk, I'll spend some time discussing how do we image the farm. So as you can understand, there are different sensors that are used in Farmbeats, and one of the key sensors is a camera. And I'm sure that all of you have seen in the news that, you know, off-the-shelf drone and UAV technology has improved by leaps and bounds in the recent years. And so nowadays, for a relatively small sum of money, you can buy a pretty reliable drone that flies autonomously. What is being shown here in this video is a drone flying over one of the farms where we test our technology. This is a farm in Carnation. And this is a downward-facing camera. The drone is flying probably 30 feet or 25 to 30 feet above the ground. And it's essentially flying in a zigzag pattern that was programmed by the person flying the drone. The drone is completely autonomous and you know, records the video on the memory drive that's on the drone. So the thing that I'll be talking about now is how can we process such videos and turn them into a more useful representation that is compact and so essentially a high-resolution aerial photo. And traditionally, such photographs have been you know, created from processing satellite imagery, or in some cases, you know, you've had special flights, you know, flying at a low altitude over some terrain. So, for example, when you look at Google Earth or Microsoft's Bing 3D maps, those applications actually processed imagery from specialized aircrafts that flew over the whole city. So what has changed now is we can fly small drones at, you know, at a much lower altitude, but we can then process these videos and construct essentially similar kinds of reconstructions of the terrain. So this video shows a result from our software. This is typically called photogrammetry, or also called 3D computer vision. And what you are essentially looking at is a sparse point cloud that was automatically reconstructed from the video. And the blue cones represent a small subset of cameras, keyframes from the video. And this was done completely automatically by processing matching features and doing geometric computations. So then from that representation, we reconstruct what we call, informally we call this an aerial map, but in the literature, in especially remote sensing, people also refer to this as an ortho photo or an ortho mosaic. So this is an extremely large resolution, high resolution image, and if you look here, depends on the original video resolution, but you know, essentially every pixel in this image is of the order of 2 to 3 centimeters. So there's a huge amount of detail here that you'll never be able to get with satellite imagery. And using a lot of computer vision techniques that we have developed in the lab, but these are also now well understood. Essentially, if you look carefully at this photograph, it was stitched from almost 400 to 500 individual video frames, but you don't observe any artifacts where you see the boundaries of the individual frames. In the middle of the scene, everything nicely blends. So essentially what you're looking at is several years of advances we have made in the computer vision field at being able to do these sort of things. Here are some more examples, and the bottom 3 examples are all taken at a farm that's near us. It's in Carnation, Washington. But the top left result is from a farm in India. I think it was captured, the video was also captured by a similar drone. And as I was saying earlier, there's a lot of advantages over satellite imagery. One of the advantages being that you can fly pretty frequently and you're unaffected, essentially like cloud cover. When you have satellite imagery, the typical refresh rate that you can get is much lower. Although companies who have been trying to put more and more satellites up there, still going to be much more costly to have them fly over the same area multiple times. And this is something you can do much more easily with drones and UAVs. So, and furthermore, these drones that are being developed, many of them are actually being now equipped with specialized imaging. So this is a multispectral camera that we have played around with a little bit, and it essentially captures imagery outside the normal visible spectrum. And so what's shown on the right side are similar panoramas that were generated with the imagery in the near infrared, that's called NIR. And there are like certain other bands which are referred to as red edge, red, and green. So effectively, the technology we have for stitching imagery works also for the images that are in these bands. So yes, and so as you see, so there's basically a lot of information that we can extract and provide to like a domain specialist or other systems that are going to then do statistical analysis or machine learning on top of these. That's sort of the goal, to enable such technologies. So then we were in the process of building these technologies and deploying. What we've also done is we've flown several flights over the same farm in Carnation, and here's an animation of the three-dimensional point cloud registered to each other. So these drones did come with GPS. So the GPS was used to get a rough alignment, but further processing had to be done to get the alignment to be more precise. This is what allows us then to play this animation. While this is just a visual result, this sort of alignment is really important when processing, longitudinal data, so time series data, and could be very useful for all kinds of, modeling for making future predictions. And then we went further and converted these point clouds into the aerial maps. So now on the right side, you see a time lapse showing what the state of the farm was. And doing this sort of thing was not possible a few years earlier, because just collecting images from the air was not something you could do that easily. So we see drones and computer vision technology as a tool that will enable a lot of new kinds of sensing or analysis from the air. So this is basically showing focusing on a small area of the farm that's changing. So the farmer could be using such tools for essentially inspecting the farm and just trying to understand what's going on with my crops. Furthermore, we have been thinking about what happens if for farmers who cannot afford an expensive drone. And while drones are nice, they do also have a limitation which is hard to overcome. It's the limitation of battery life. So if you are in a large farm in the US, it's actually pretty challenging to cover the whole farm in high level of detail using one battery charge. So there are reasons to investigate other ways of capturing images from the air. And what we've basically been doing is we've been experimenting with helium balloons, helium-filled balloons that stay up in the air. So essentially, this is a kind of weather balloon that will stay up in the air for a pretty long period. And we've done some initial experiments in India where we've had people on the farm walk with a tethered balloon, essentially walk around on the ground and moving the balloon around. And then we use similar technology as I described earlier to process those videos and turn them into an aerial ortho mosaic as shown on the bottom right. So while this can be done with a person walking around, other options involve even like, letting the balloon record over a long time period and monitor from the sky. So these are other things that we at MSR have been looking at as part of the Farmbeats system. Yeah.
Sudipta?
Yes.
You have actually addressed the question, I think, to some extent by Jim on the chat window. Jim asked, well, drones seem great for small farms, hundreds of acres. the median farm size in the U.S. is 2,800 acres. How does this scale for 4,000, 5,000, 10,000 acre farms? And as I said, you seem to have addressed some of that, but maybe you'd like to elaborate.
Yeah, I think that, Jim, good point. There is a scalability issue. I think the way to scale it up is you have some trade-off between the pixel resolution you can get and coverage and battery life. So those are the three things in conflict. If you want to cover 100,000 acres, essentially for the same drone, for let's say a 15-minute flight time, you'd have to fly much higher. And although we haven't done too many experiments yet, a lot of the drones can actually fly pretty fast. We just haven't been flying fast because the video could get degraded. So if you fly faster and if you fly higher, each frame of the video sees more of the farm. So you can actually solve this computational problem and come up with the right settings so that you optimize coverage versus resolution.
Yeah, I also wanted to add to it. So one of the other things we did last year was we used a fixed wing over one of the farms. So fixed wing flights can go, they are more expensive. They'll be $8,000, $10,000 for the flight, but they can cover really large areas because they're using fuel. The other thing we are also exploring with drone companies is alternate agricultural drones. So once we're talking of really big distances, so those are two. And the third, because I know there are a lot of researchers in attendance, one of the problems is, can you use multiple drones or a swarm of drones to cover it? This is still in the research phase. There's some really interesting work coming out of UPenn, but that would be another idea which we'd love to explore as to, can you use a combination, multiple drones, or can you, if you have a fleet, what is the algorithm based on which you can cover much larger areas? And around that, there's another startup here too, which we are working with in Seattle called Vibotic. This is out of Josh Smith's lab, which is using wireless charging out in the middle of the farm. So once these autonomous drones are allowed without a human pilot, you can think of scenarios where this drone would fly, go on this wireless charging pad sitting in the middle of the farm, charge itself, and then go forward. That's the future that we envision with this technology.
So there's another question. Let me read out the question. I like the helium balloon solution. What sort of thing can you capture using computer vision at a higher vantage point that does not need sensors in the ground? Can you detect soil moisture? Anything the drone would miss that ground sensors would only capture?
Yeah.
So actually, we will be addressing this in just the next few slides, and we've done some preliminary experiments in this direction on how to combine sensing from the ground and sensing from the air. And maybe let's present that, and the person asking the question, maybe you could ask us once more if it addresses your question.
Right. So Yuvraj, in particular, just to elaborate on what Sudipta said, so we'll talk a little bit more about it, but things like soil moisture, you can't really detect, like 6 inches below soil, what's the soil moisture? You can't use this aerial image for that. Aerial images are a good proxy, but they're not giving us the ground truth. So that's why we need both aerial images and ground sensors.
Okay, so we'll return to the screen share right now. Just give us a second. Can everybody see the screen again?
Yes.
Okay, so we'll continue. Moving on, this is essentially now we are basically I'm going to briefly talk about certain things we are exploring where we want to address the issue of how can we now still produce high resolution precision maps when you have a lot fewer sensors on the ground. And as Ranveer mentioned earlier, there are various reasons for this. The sensors themselves can be expensive. If you put too many in the farm over a long crop season, they would be hard. They could be hard to maintain, and there might be other kinds of farming constraints which limit how many sensors you could put. So what we wanted to do was essentially try to come up with a new a method that would try to fuse aerial imagery with ground sensor data and make predictions at a slightly higher resolution that would be possible with only ground sensor data. So the approach that we investigated is the following. It uses a standard technique in machine learning called supervised learning. The high level idea is that at the locations on the farm. By the way, all the imagery that I have been showing you so far, I have not mentioned it, but because the drone comes with GPS cameras, the imagery can actually be geo-registered in a geospatial coordinate frame. So on every pixel, you sort of can go and ask, what is the precise GPS coordinate of this pixel? And the sensors that were used at the farm also came with GPS sensors, so you know that what the precise location of those sensors are. So an example is on the right side, where I'm showing for that panorama that was stitched using our system. So the ortho mosaic, those are the corresponding, those red and yellow dots represent the location of the sensors. So next, what we can do is we can record data from those sensors, and from a orthomosaic computed at around the same time, we can now compile a data set of image patches and corresponding sensor data. So represent that with X and Y. And the machine learning approach here is we want to essentially try to predict the sensor values given an image patch. So the particular machine learning model we used is called a Gaussian process. There are other models you could also have used, but this one is particularly nice to train. And intuitively, you can think of what we are trying to do is we are trying to sample a function. The function is essentially this precision map, and we are trying to sample the function at sparse locations and then trying to interpolate in a smart way. And the intuition is that areas of the farm that have similar visual appearance are more likely to have similar sensor values. This is what the machine learning model allows us to predict. So once it has been trained, you simply apply this model on patches in the image. You essentially run the prediction at multiple locations in sliding window fashion over the whole image. And this is what produces this precision map shown on the bottom right. In this case, I think this map is showing soil moisture. And, pH. So I'll now hand it over back to Ranveer, who'll talk about some of the other challenges in Farmbeats.
So just to add to what Sudipta said, the reason, one of the other things about this particular technique is so cool is right now, the state of the art in agriculture with sensor interpolation is people would use something like if you deploy a few sensors, like if you wanted to build a soil moisture map, you put a sensor, say, every few acres, and then use linear interpolation or Craiging's formula to actually do the interpolation, which is known to be very inaccurate. And in the paper, we've compared with state of the art. Here, instead, what we do is using the aerial image as a backbone, we are then able to, in addition to the Craiging's formula, you're able to do better interpolation because you're using these visual features. Visual could be RGB, multispectral, or hyperspectral, to do this kind of interpolation. And that's why in the startup space, there are a lot of companies talking about sensors, a lot of them talking about drones. We believe this is the first time we're able to combine both of them in a meaningful way. So I think there was another question I could.
Yeah, quick, short question. Which band measurement was used to predict pH?
Yeah. So here what we're doing is for pH, we took the actual sensors on the ground, and then we did the interpolation using RGB as the first level. RGB images right now, what we're looking at is using the red edge as a predictor, and also looking at other bands in multispectral to do better predictions. But the point is that, so the way to think of it is that we still rely on ground sensor data as the raw truth, raw ground truth. And we're using these images, these visual bands, as just an interpolation framework as opposed to the ground truth.
Yeah. So in other words, you would typically run the training every time you do a new flight. You could retrain this model and essentially have a new model every day that adapts to the conditions on the field.
Right.
It's computationally extremely efficient to train and predict. So
right. So the next challenge is that of internet connectivity. The problem is the following. So we showed how you could gather a lot of data from the farm, send it to the farmer's house, but the connectivity from the farmer's house to the cloud is weak, and it's also prone to outages. Most of the farmers, they pay for broadband, but all they get in the farm is 1 to 3 megabits a second. That too, I'm being optimistic. And it's also prone to outages. There's a farm in upstate New York where we do our deployments, and every time there is a snowstorm, there's a high likelihood that the internet connection will go off. So then how do you build a useful system for the farmers? So before we did that, what we did was we went and did a survey with several farmers, professors, agriculture agronomists, companies, to see if you could do what Farmbeats could do, collect a lot of data from sensors, from drones, and combine them in meaningful ways. What kind of services can you then provide to the farmers or to the stakeholders? I'll walk you through a simple example. Suppose these are the different sensors that are out there, like you could get weather data, images, videos from drones, you could get image stream from cameras, sensor data, for example, moisture, temperature, and so on from the sensors itself. We have an app for the farmers, and this app itself is another sensor reading. It's unstructured data, but it's still giving you information about the farm. Just to walk you through an example of the kind of services we can provide, from the drones, images, and videos, you could build the ortho mosaic, like Sudipta mentioned. You could then combine it with the sensors, like you previously talked about, to build, say, a heat map, say a moisture heat map of the farm. From a few moisture readings and the aerial image, you can build a moisture heat map. Once you build a moisture heat map, you can then look at the predicted weather forecast and then come up with an irrigation schedule of when do you water, where do you water, how much do you water. And this is just one example. In fact, when we talk to people, they came up with a huge list of examples. And in fact, this is still dated. Now, every time you present to a new company, they come up with many new scenarios that they could use it once you could start building such a framework. So the reason we went through this exercise was to see what are the characteristics of the services that we can offer. Like, for example, this is for the farm in New York. On an average, this is the amount of information you generate on a daily basis. Shipping all this information from the farm to the cloud is expecting too much, gigabytes of data. Actually, you don't need to, because depending on the service, you have different latency constraints. Like, for example, I apologize for this is livestock monitoring. So you could be if you want to query sensor data, you probably want that information in seconds. If you're doing livestock monitoring, you also want that information in seconds. There's an interesting example here. There's a farm in Carnation, which is 25 miles east of Redmond, the Microsoft campus. And the farmer there, he's a smallholder farmer. He has a 5-acre farm, and he sells his produce to the restaurants here. He has an interesting problem. Every time, just before harvest, there is a bear, a black bear, not a grizzly bear, not the wild bear, but still, it's a bear that comes and eats up all the red lettuce in his farm, doesn't even touch the green lettuce next to it. And Sean, the farmer, his problem is, hey, can you send me a notification when the bear shows up? Now, sending that notification a few hours later will be too late. So what he'll do with it is a different question. He could come with a gun and scare the bear away. But the point is, sending that notification, you want to send it in seconds. You don't want to wait an hour or 2 hours before giving that notification. But for some of the other applications, like irrigation scheduling, you would wait a few hours. For pests, when to apply pesticide where, you could wait a few hours, even a day. For variability analysis, what do you plant, where and when, you could wait days, even weeks before giving that information. In the typical world, as I said, you would ship all the information to the cloud, do the analysis there, and send the information back. But that's not an option because of these two reasons out in the farm. So our key insight when we were building this was that most farmers have PCs. If they don't have a PC, we have a Windows 10 IoT enterprise box, which runs on Azure IoT Edge, which you just ship it to the farmer. And it could do a lot of computation on the farm itself and send insights to the cloud, where we could integrate with other sources, other information sources, to provide recommendations to the farmers and analytics to the various stakeholders in the agricultural community. Just taking a step deeper into this, what is this gateway? So everything inside this blue box here runs on this PC. It ingests data from sensors, it ingests data from drones. Once it gets this video, the ortho mosaic generation code runs on the PC itself. One of the things that I was mentioning was, this is a code that is several years of work at Microsoft Research. We were able to make it run quite fast, running locally on the PC itself. If you've been using drones right now, the state of the art typically is, you'd fly this drone, you would take the SD card out, go to a place which has great internet connectivity, upload the video, and then do the stitching in the cloud, and you get the result back. With this, even for a 30-minute flight, we're able to generate this ortho mosaic in about 30 minutes of time. So this ortho mosaic is generated every time you fly the drone. And you generate the ortho mosaic and use it to build the machine learning models. But every time you get new sensor readings, every 10 minutes or every hour, you have an up-to-date heat map for the farm. This heat map, like the one we showed for soil pH or soil moisture, would then feed in to these ag services. The ones in blue are the ones we built, the ones in white are the ones we're working on. Actually, we've made quite a bit of progress on the pest infestation here. But this is where we need expertise in agriculture, where we work with the university professors, with the ag companies to build these kind of services, these kind of analytics. The other interesting scenario we have is cameras, and I'll show you one scenario where we use cameras. We have this deployed in a barn in New York, where they stream the videos to the gateway again, where we're running deep learning on the gateway, on what's happening out there in the barn. All this information is lazily synced with the cloud, so it doesn't stay at the edge. We lazily sync videos, all this information to the cloud. And the other interesting stuff about this gateway features are it can run offline. We have cases where this has been disconnected for a month and we've still been able to collect data. We have storage, offline storage here. And the interesting thing is the high-res drone videos is not something that we aim to ship to the cloud. We transcode it and ship the low-res versions of that to the cloud. But from computer systems researchers who are there in the audience, there's a very interesting paradigm that this leads to. Typically, when we think of cloud services, we are accessing all these cloud services. When you think of services, they are hosted in the cloud, like your email, like going to news sites, because all the data resides in the cloud. Now, this leads to a very interesting paradigm where you have unique data that's residing on the edge, here on the gateway, like you have this high-res drone video. So you could have unique services now, which are only running on the edge and not in the cloud. One such service which we built is a 3D walkthrough of the farm. So because we have a high-res video sitting on the farm, and as Sudipta talked about the 3D model that we have developed, you can actually build these kind of very interesting services because the data resides on the edge. These services will be running on the edge as well. So when you hear a lot about IoT gateways, but on the bottom left are some of the features which we think are unique. That is, this is running on Azure IoT Edge. All of these are running in Docker containers. So the benefit there is if the connectivity is great, you just migrate this component to the cloud instead of running it on the edge. So this is what we're building as part of the Farmbeats gateway. On power, so we had an NSCI paper where we talked more about power and the kind of things we've done there. One interesting thing that we did was we have an IoT core device that's sitting out in the farm that would look at the predicted weather forecast and based on the weather predictions decides if it's going to be cloudy, it runs the entire system slower so that your system can actually last longer. That is one way we are dealing with variable solar power. We are working with University of Washington here on using RF to power the devices, just like we talked about how we use the TV white space antennas in the middle of the farm. Those TV white space antennas transmit at high power, so we can use them to be powering the sensors instead of having batteries in them. Another interesting work we did, which is in the paper which we did, the intern was from Purdue, and after he went back, we continued working. And the key idea here was to leverage the wind to change the yaw of the drone so that you use the wind to accelerate and decelerate. So one of the big problems, as Sudipta pointed out with drones, is battery life. Most of the commercial ones will last for, say, 30 to 40 minutes. That too, we're being optimistic. In order to make them last longer, the key idea was if you can use the wind to accelerate and decelerate, you can improve the battery life. And in the paper, we show that this can result in 30% improvement in drone battery life when the wind was between 5 and 15 miles an hour. So we have, now I'll talk a little bit more about the deployments. We have 3 non-commercial deployments. Right now, we are starting to move to work with companies and doing more POCs and commercial deployments. But the non-commercial ones, the ones we actually work with directly with the farmers to see what kind of benefits we can provide. So we have 2. One of them is in Carnation, which is 25 miles east of here. If you're in the Seattle area, I would love to take you there for a visit. We do a lot of tours, a lot of people are interested in seeing what we're doing. We're working. So these are 2. The one in India, we started 2 of them. One is in Anantapur in Andhra Pradesh in India, working with the Gates Foundation on that one. So the 2 farms, at least in the US, the one is 5 acres, the one in Carnation, he's a smallholder farmer, and the one in New York is a 2,000-acre farm. We have the various statistics out in the paper as well, but the key thing we are very proud of is, even though there was a week-long outage from a thunderstorm, our system continued to run, gather the data in the middle of the farm. The kind of insights we can provide are, this is, for example, the farm in upstate New York. This is a 4-kilometer stretch. The farmer wanted to know how his cows are doing once they were out in pasture. We could flag things like the grass is growing back well. This is a water puddle that needs to be fixed before the next planting season. This is the cows are pooping well, which is also important information for the farmer. This is fertilizer for the farm. This is where the cows are. This is a stray cow that needs to be herded in. All of this being done on the gateway can provide information within 30 minutes as opposed to taking a very long time to produce this kind of data. So this is for the farm in Carnation, the kind of ortho mosaics we can provide these pretty pictures to the farmer. We can also overlay it with data. For example, this was one of the moisture maps we had created for the farmer. As you can see, the top left part of the farm, we were able to flag that this part of the farm is moist without having a sensor over there. This is a pH map like the one we previously talked about. This is after the farmer had applied lime. We were able to flag that these parts of the farm are still acidic. Now, the question you would ask is how accurate would these predictions be? So what we did was we captured over 1,000 measurements in 2 different farms, 2 different 5-acre plots. One was in Carnation, the other was in upstate New York. And what we said was, if we took just 10 sensor readings, how accurately can it predict the 990 other values that we had sampled? This is ground truthing with actual sensors in the ground. And this is how accurate the system was. We looked at it for 3 parameters: temperature, pH, and moisture. And this is how accurate Farmbeats was in predicting the 990 other values based on the 10 sensor points that we picked. And this is how accurate the sensors were, in the sense that the temperature sensor would report temperature in 1 degree Fahrenheit, and pH would report it in 0.2. We are not claiming that Farmbeats is more or less accurate than the actual sensors itself. The thing we are claiming here is that the results are so close to the actual measurements that anything we provide based on this, we believe, is actionable by the farmer. And that's something right now we are validating this over many other plots as well. Right now, this was just over 2 plots. One of the other things we're looking at is, if we can do it here, can we leverage the same technique to start building heat maps over satellite data? Right? Can you use? But that's still work in progress. So the key thing here is that we believe that this is, and in the paper we have another interesting evaluation scenario here, where we compare this with existing state-of-the-art techniques of using Craiging's formula, for example, to do the interpolation, how much more accurate this is, and we show that it's 3 times accurate and so on. Now, when she gave it out to the farmers, the farmer in New York, he wanted to use it for another scenario, which was much simpler for us. He was like, hey, I have these 8 refrigeration units, which are pretty big refrigeration units where he stores his produce, and people accidentally leave the door open and the produce goes bad. So he was like, can you help us monitor that? That was an easier problem for us. We use the white spaces, we have sensors, we then look at that data and flag when just it's an anomaly detection problem. This is a deep learning scenario where we have cameras in barns streaming data over the white spaces, and we have this cow detection algorithm. We can count number of cows, how many cows are there, where they are moving well, and so on. So at a high level, that's what Farmbeats is. It's an end-to-end Internet of Things system, which is able to ingest a lot of data from the farms that previously people weren't able to gather using TV white spaces, using aerial imagery and the sensor fusion technique, and the deep learning and the machine learning algorithm that goes on top to provide interesting insights for farmers. And these are the farmers we work closely with, and they've been really amazing, and they've been very helpful educating us on farming and farming system. Be dealing with lots and lots of outages that these research prototypes have. So to conclude, this is our system. You can go learn more about our system on this website. And of course, this work is done by several people here and really stellar interns. Without them, we wouldn't have been able to do what we're able to do here. Yes,
well, thank you very much. This was wonderful. So I would direct you to the chat window. We have questions from Jim, Norman, Ying, and Connor that have been sitting there a while, and Aaron just added one. Maybe you could address those quickly, and maybe we'll take 1 or 2 from the audience before we break.
Okay. So this one we answered, the pH one. What is an example of?
So Jim asks, what is an example or two of visual features that correspond to interpolation of moisture or pH?
Yeah, so here we are looking at RGB, just the pixel values. In addition to that, now we are looking at multispectral features as well, multispectral and hyperspectral. Does that answer the question, Jim? Or
I think that's probably good.
okay.
Any work on use of sensors on plants to, for example, sense water stress?
That's a very interesting one. Yeah, that's a very interesting one, and we would love to explore this. And there's some work that has happened at Cornell, and anyone else, if you have any knowledge of that, would love to go talk and look at what it is and incorporate it as part of the system. There's another work recently that we're working with Pat Schnabel at Iowa State, and he was talking about some sensors, nutrient sensors that we built. That's another thing that we're looking to do. But sensors on plants would be amazing. That would be an awesome thing to add.
I would say that in the history of machine learning, one of the most famous domains explored back in 1980 or even earlier was by Richard Mikalski on soybean disease. It would be interesting to go back and revisit that work, except with your technology for image processing.
Would love that. Yeah, I think that would be really cool. Yeah.
Ying asks, since the training is computationally expensive and big data is needed, how many data were used for training given the infrequent UAV measurements?
Right. So training in this case for this particular is not that computation. That depends. Is it for the Gaussian processes stuff? So that's not as computation intensive. Yeah. And
actually, the pre-processing is a bit expensive, but still something that runs in we would be able to process like a 3 or 4 minute video in under an hour easily. Yeah. So that's the pre-processing that you would need to get accurate, like the map of the environment. And so then the training data for this GP is actually quite small. It's pretty sparse. It's just the patches. We need several hundreds of pixels, probably more, several thousands of pixels at each location. But then the number of sensors in our case were on the order of 10, a dozen.
And the thing training. And we intelligently place the sensors as well, rather than just randomly putting the sensors. We use that. We use a sensor placement algorithm to decide where to actually put these sensors.
Let's see, a question on the precision map. What is the spatial resolution? What accuracy are you mapping to?
Yeah, so this is variable. So we allow this as an input to the system as to what actually. It also depends on the resolution of the camera itself. But this is something which is variable. We actually put this as an input to the heat map generation algorithm.
So it will be quite low. Like the factor in the resolution would be at least at an order of magnitude lower.
Yeah.
But it would still, I think, we need more evaluation, but we think that it can potentially be more accurate than satellite imagery, because the raw imagery is at high resolution. So the texture of the grass growing on the soil is something that the model would capture. Sorry, the aerial map would capture. So the GP would potentially be able to exploit more high resolution input features than would be possible with a satellite image. But satellite images obviously provide you coverage over huge areas, which would be impossible with the drones. Or so it's. I think there are some complementary.
Yeah.
There's another question. The next question is from, is it possible to use uncertainty information from the GP graphical model to recommend sensor placement? That's a great question. Yes, indeed. One of the advantages of Gaussian processes is that it allows you to make mean predictions, but you also have the uncertainty, the sigma that essentially tells you where you are missing, where there's more uncertainty. So if you had to place the next sensor, that would essentially, this would be a great way to decide how to do it. You probably have to run the training over several epochs, several flights, so that you because the information could change from, let's say, week 1 to week 2. But something like this could definitely be done, I think.
So I'm encouraged by the number of questions we're getting. So I'm going to let us go 5 minutes further, even though we're officially out of time. So why don't you take a couple more, and then I've got one, and maybe somebody in the audience has one.
Okay. Have you done any analytical work combining data layers such as soil moisture sensor location with soil maps or results from soil tests? Any efforts in cross-sensor multiple drones? So we'll answer the first one first. So the first one is, have you looked at combining data layers such as soil moisture sensor location with soil maps or results from soil tests? So we use the USDA. So we're working with USDA and some of the pilots around this, where we take their NRCS soil data to actually do. So we're looking at different nutrients and soil chemistry, the chemical composition. But this is still in research phase. We haven't taken it. So the predicting soil nutrients and building heat maps for soil nutrients is still in research. We haven't come up with the final answer to that yet. But
I would like to inject a question from someone who hasn't asked yet. This is on the Q&A board. Regarding Gaussian processes, is this method affected by different types of plants growing on the farm? How do you work around rows of soil versus rows of trees?
Yeah. So we first focus only on the part where there is crops, and each crop we would be addressing them differently. Now, a side question around that is what happens when the crops grow? You're not really seeing the soil at that point. So one of the things that we found is that our predictions were still accurate even when the crops grow, because I think plants are kind of reflecting what the soil properties are, and like plants are sensors themselves. So they're reflecting kind of the soil properties, but I think that's where the in-plant sensing thing that someone mentioned earlier, that would be very interesting. If we could do plant sensors.
Also, just revisit some of the work we did with multispectral data. I think that, so there's definitely a lot of room for future work. And as part of the what we presented was part of a paper at NSDI. I think the first challenge was to put the end-to-end system together that lets you collect data in a completely automatic fashion. And I think now it's time to revisit some of the machine learning
make it more accurate
analysis to understand what works, what
right. I think with Gaussian processes, so the key thing there was, can we use aerial imagery to do better predictions? And suddenly we've seen that it's better than not using it. And GP was a very good first step. The next thing would be, can we make these algorithms even more accurate? And we're seeing a lot of interest there as well. And we are working ourselves on those problems.
So Microsoft has a history of work that relates to the developing world. I remember going to a symposium co-chaired by Eric Horvitz on AI for development. And which of these technologies do you think that you're looking at would be transferable to the context of the developing world?
Yeah, so we are working on the Farmbeats is something where we have a big initiative in India as well, in India and Africa. Africa is something we are starting in India. We are actively engaging on this. We have researchers in Microsoft Research India. We have developers in Microsoft India working on the Farmbeats system. And we are also working very closely with the Gates Foundation on taking this to the Indian farmers. Like, for example, the scenario that we have is, one of the things we did not talk about is, because the sensors are low cost, you can start doing microclimate prediction for the farms. And based on that, once you provide that information to the agronomists, they can make recommendations for things like when to sow the seed, what pest is likely. And we built the entire end-to-end service around this. One was a sowing app that we built, where if it's, for example, if you know that it's going to rain in the next few days, that's not a good time to sow your groundnut seeds. And this we did in working with ICRISAT, which is a CGIAR organization. And it was a study where it showed up to 30% improvement in yield if they followed that. And so these are the kind of services that we're building for India and Africa and the developing world, and trying to take it to the smallholder farmers.
Okay, very good. I think we are definitely over time now. And so I think we're going to break after giving you one more applause.
Thank you.
And this was really active. We have some questions that went unanswered. So hopefully, the people who had questions can email you.
Yeah, yeah.
I expect that you'll hear from some people. So thanks so much, everybody. And we will reconvene in 2 weeks with a talk by Tanya Berger-Wolf. Bye-bye.
Thank you.